Bismillah ar-Rahman ar-Rahim. Good evening, guys. Today will be the lecture number 3, but part 2. At part 1, we illustrate important information about the bones layers, the bones shape, what's the related between the bones shape and the immune function. We was talking about the bone layers, why the bone has the strong shape, strong behavior, can take overload weight, some important information about the layers, what the main reason make our bones strongest, what is the related between the spongy bones, what's the reason of it, what's the benefit of it, and we was talking about the disease, about when some guys, some man, women, doesn't matter, over than 35 years old or taking a lot of smokes, alcohols, what will happen to them and how we can solve it. Now, our topic will be different. Today, I have a question. We have a bar of material like that pen. When we put a load, the overload on it, what will be before reach the fracture point, before reach the breaking point? Some change and its length will be how much steps will pass to can reach the fracture point. By these few slides, we'll try to solve this answer, and we have another answer. What this bar material will severing from it? Any similarity with the bar material and bone, our bones? If our bones will sever from the same effects about this load, let's try to solve this question. Now we have two questions. We must solve all of these by using these few slides. Here the contents, we will focus on the stress strain. It's important curve like at the lab when we was talking about the IV curve, when we was trying to solve the specific resistance by using Ohm's law, was plot, we was determine the slope by using IV curve. We will do the same thing here. The stress strain curve will be very important to illustrate how much steps we have before this material bar reach the fracture point. And the stress strain stage, the equation of U capital and what that's mean, the stress strain stage of bones, stress kinds of material and bones. Now let's start about, take a look to this stress strain curve. Contains from what? It's a behavior of material when it's subjected to load. It's the behavior of material, behavior of this bar material when subjected to when we put a load on it. From this side doesn't matter. This material bar will facing some change in its shape. In this diagram, stresses are plotted along the vertical axis, and as a result of these stresses, corresponding strains are plotted along the horizontal axis. Stress, when we can act as a weight, strain is the sharing weight on this material, bar material, Okay, let's take some specific details. Here I have many pictures. The first one illustrated to us the Hooke's law. Specifically, the change will be on the length. By increasing the weight, the change on the length will be bigger and bigger. Here we have some kinds of stress, not just to increase the length, but maybe in somehow will decrease the length. And the last one will be with a pair of reverse strong power. Let me say it's more specific. Pair of a mix of power, a mixed direction of power at C. Here, from the diagram, I mean stress-strain diagram, can see the difference marks points on the curve. It's because the ductile material, it's a material with some specific characteristics, like melt steel, is subjected to tensile test. Here we have some stages before reach this bar material to fracture point before breaking down. Proportional limit is the first one here. It's from O to A. That means we increase the stress from O or from 0 to A. Elastic limit or region, it's the B point, or we can say yield point. That means we will increase the stress more. All of these will be at elastic region. What does mean elastic? That means flexibility region. That means we can imagine the material when uploaded, the load from it can come back to its original shape, original length. Okay? Ultimate stress. Here we can take a look to the stress. Here the stress is decreased a little bit, but here at C is started at plastic region. That means we have a little opportunity to this material to come back to original shape. Breaking stress. This will reach when the stress is increased more. The last one is fracture point or breaking point. That's mean here until here the material bar will break down. At last, E is the fracture point, like I said before, or plastic region. At plastic region, sorry. The plastic region is starting from B, like we take a look, like we are looking here, from B to E. All of these are elastic points, sorry. Here, let's illustrate with some specific details all of these 4 or 5 steps. Let's start from the first one, proportional limit. Proportional limit, the A. Here, we have increased the stress to reach this point with smaller change in the strain, okay? Proportional limit point, it's point A on the curve up to which the value of stress, proportional limit stress, and strain remains proportional. Strain at x-axis remains proportional with small increasing according to the stress. Here we can say this change, we can illustrate this change by using Hooke's law. Why? Because from O to A, it's almost a line, not pure curve, not clear curve, okay? Hooke's law of proportionality from diagram can be defined between point O, A. Why? Because a straight line, almost straight line, which shows the Hooke's law of straight strain is followed up to point A. Hooke's law, the great example to Hooke's law is the spring. Here, that's mean we will face change at the length, at its length, okay? No more. Specific at its length. X maybe will be 2x with overload, or maybe will be half x or 0. That's according to the weight we are using, okay? What is the Hooke's law? Let's take a simple idea to it. F, that's mean force by Newton unit, equal minus K is the elastic of the spring of the material, and it's changed from 1 to 1. X is the change of its length. Here, let's change from proportional limit to elastic point. What is the difference between them? What is happening them? At first, it's clear the stress is increased more than at proportional point, with little bit increase more on the strain, but it's still at elastic region. That means we have opportunity when uploaded the load, the shape of this bar material can come back to its original shape. Elastic limit or yield point, we can say, is the limiting value of stress up to which the material is perfectly elastic. Like I said before, has opportunity to come back to its original shape. From the curve, point B is elastic limit point. Until closed the B point, the elastic region will be done. We will start at another region. I will illustrate it at the next slide. It's the plastic region. Why is called elastic limit? Like I said before, because the material will return back to its original position if it is unloaded before the crossing point B. When crossing point B, what that mean? That mean we are started at plastic region, and here the conditions are different. This is so because material is perfectly elastic up to point B. Note elasticity, what that mean? It's the ability of material, like flexibility. It's the ability of material to retain to its previous shape after stress is realized. Here at point C, that means we are started at plastic region, not elastic region. That means the shape will not come back to its original anymore. Ultimate stress at C. Here, by approximately the same stress amount or little bit less than, we can take a look to C point. Like I said before, with these few difference, the stress is approximately at elastic point or little than less. Ultimate stress, C point. What is this? It is the stress after which material extension takes place more quickly with no or little increase in load. What that mean? No or little increase in load. That mean no or little increase in stress. And I explain that by using this red arrow. When reach C point, if it is unloaded, the material will return back to its original position or not? Definitely no, because we close the elastic region and now we in another region. This region is a plastic region with no opportunity to its shape to come back to original shape anymore. D is the ultimate stress point, or we can say breaking stress point. Ultimate stress, that's mean, well, I think it's no more than, it's the maximum strength. The maximum strength which this bar material will suffer from it. No more. After that, this shape will not just change, no, but will break. That's it. No more ability to can sever this heavy load. Is the maximum strength that material has to bear stress before breaking. It's the stage before fracture point, before the breaking point. No more maximum strength will be after load another or put more heavy weight. This material bar will break down. After point D, material has zero strength change, like I said before, to face further stress. No further stress can take this bar material. No plasticity, it's the reverse of elastic deformation. Here are the last, the fracture point. We have some important information about it. Let's talk about them. Breaking stress or fracture, it is the point where strength of material breaks on the strain curve, on the stress strain curve. Point E is the breaking stress point considered to a bar of cross-section area. When I broke this pencil, this pen, to two parts, all of them will have this A. That's mean the cross area to this bar material. Is the point where strength of material breaks on the stress strain curve. Point E is the breaking stress point. Consider a bar of a cross-sectional area being subjected to equal and opposite force pulling at the ends, so the bar is under tension, under heavy weight. Now, let's talk about what is the stress, what is the strain, what equal the stress divided on strain. At first, let me start from question number one. The material experiencing a stress. Sure, because we put it heavy weight on it, defined to be ratio of the force, F, that's mean force, with Newton unit, to the cross-section area. That means stress here equal force divided on the area. That's mean the stress I'm talking on here. The stress equal the force divided on the cross area, the cross-sectional area to this bar material, this one, this square. It's not a condition to be square. That's according on the material shape and the load, heavy load, heavy weight, like you want. Here, stress, like I said before, equal F with the Newton divided on the cross-sectional area by the stress unit will be Newton divided on meter square. The shear strain, the shear stress or strain, we can say shear stress. It's the change on the length divided on the original length. Let's take a look. That's mean we can say the strain or shear stress, delta L divided on L, equal equation number 2. By divided stress on strain, what we will get? The Young models from U, it's equal stress divided on strain, by that F divided on A divided delta L divided L, original L, will equal F multiple L divided on cross-sectional area multiple the change of the length. Strength of material, a note, its ability to material. Here, not like it's the flexibility length of material. Its ability, now, yes, it's better to retain the flexibility strength of material. Its ability of material to withstand and applied load without failure or plastic deformation. That means without broke or some change in its shape will happen. Here, let's make a golden link between the principal physics and the medicine medicine field. What is this golden link? The bone is material and it has a shape and is stuff, has many layers, give it this shape, this tough, this hard characteristic to load overweight. All of these has some similarity with the bar material. Let's take a look. Yes, the same stress strain stage to the bar material, the same these stages. The bone is habit. All of these stage 2 material will be to the bones. By that, to any bones before reach fracture point, before reach breaking point, will suffer from the same stage. First one, proportional limit point, and we'll straighten it by using the Hooke's law because almost it was line. And elastic point, B, and it's the last point at elastic region. Ultimate stress with it's the first point started at plastic region, and it has a no or little bit change in the strain and the shear force. Ultimate stress point is the D, and it's the last point has some change in the length. Before D, after D, we will not have any delta L anymore. At breaking stress, the bone will fracture, the bone will break down. Here, the stress kinds of the material. That's mean, sure, this bar of material will not severing from stress from one direction. We have 3 kinds. The first one, up to down. Next one will be down to up. The third one will be pair of opposite forces. Let's go to the names of these stress kinds. The first one is compressive stress. That's mean the stress state caused by an applied load that acts to produce the length. The compressive to reduce the length because will be 2 forces on this bar material with opposite direction of the material along the axis of the applied load it's a good example to take the pushing force like figure A. Second one at B is tensile. That means we have two forces too, but here all of these two forces at reverse position. And the good example to it is pulling the material. Last one, shear stress, is pair of opposite forces acting along parallel lines of action through the material at figure C. The last one is stress kinds of bonds. The last three kinds of stress were to the bar material. Now, the same stress kinds of bar materials are to the bones. What can happen to the material can happen to the bones, human skeleton, from all the stress strain stage. That means we have three: compressive with to decrease the length, tensile to increase the length. Shear stress is a pair of forces with different direction. That's it. Have a good day. Thank you for listening or watching. See you in next lecture. Let me stop it.